Hello and welcome back. In this video we will be looking at the derivatives of logarithms. So previously we've seen how to differentiate exponential functions, and if we take the derivative of a to the x power, this is going to be a to the x power times a constant, which is going to be the natural log of a. So it's nearly the same thing. The derivative of an exponential function is just going to be itself times this extra factor. This is just some number, the natural log of a, whatever that is. When we take the derivative of a logarithm, we're going to get it's something a little bit different, but there will be a little bit of a pattern in here. So the derivative of the log base a of x is going to be 1 over x times the natural log of a. So unlike the exponential function, where the derivative was nearly equal to itself, but just kind of constant, the derivative of a logarithm is going to be 1 over x, but we still get that constant showing up, this time in the bottom of the fraction. And so in this first video, I'll just do a bunch of examples using this rule. So for instance, if I take the derivative of log base 2 of x, this is going to be 1 over x times the natural log of 2. And that's it. That's all there really is to it. If I take the derivative of log base 10 of x, this is going to be 1 over x times the natural log of 10. I apologize, my L's look like 1s. This is just something that I have to be a little bit careful with, so that we understand when it is a natural log. So here I've got the log base 7 of x squared, and I want to take this derivative. So again, what we'll notice is that we have a chain rule going on. I have the log base 7 of x. This is sort of the outside function here, but on the inside I'm plugging in an x squared instead of an x. So I've got my outside function, I've got my inside function. So I take the derivative of the outside function, which is going to be log base 7 of x. So this is going to be 1 over x times the natural log of 7. Except that instead of plugging in an x, I'm plugging in my inside function. So instead of an x, I'll have an x squared. So this is the derivative of the natural log of 7 with an x squared plugged in. And then I need to take all this times the derivative of the inside. So again, this is just the chain rule. We just take the derivative of the outside, plug in the inside function, and take it all times the derivative of the inside. To simplify here, I'll get 1 over x squared times the natural log of 7 times the derivative of x squared, which given away is just going to be 2x. So if I simplify this, I've got the 2x on the top of the fraction, I've got an x squared over the natural log of 7, and some x's cancel out, and what I'm left with is 2 divided by x times the natural log of 7. So that was fairly straightforward. We had to use the chain rule because we had function composition. We had a function inside of another function. However, using our knowledge of logarithms, we could have done this in a little bit simpler way. Notice that if I write log base 7 of x squared using the power rule of logarithms, this is the same thing as 2 times log base 7 of x. I can bring the power inside of a logarithm out front. This is something we did earlier in the semester. So if I take the derivative of log base 7 of x squared, this is just the derivative of 2 times log base 7 of x. Well, I can pull out a 2, and then the derivative of log base 7 of x is 1 over x natural log of 7. And I get the same answer. 2 times, 2 over x natural log of 7. This is 2 over x natural log of 7. You get the same thing either way. So if we can simplify a logarithm, maybe that would be easier than trying to use the chain rule in this instance. But both ways work. Let's look at another one. Let's look at the derivative of log of x squared plus 1. Again, when there's no base here and we just write log, this is going to be log base 10. And furthermore, we have this inside function in here. So a lot like what was up here, where I had just log base 7 of x squared, here I have log base 10 of x squared plus 1. So I've got that extra plus 1 in there. So I can't quite use the same trick that I used this last time. So we've got log of x, and on the inside we've got an x squared plus 1. So we do have our outside function is our log, and what we've plugged into it is now going to be x squared plus 1. So if I take the derivative of the outside function, I'll get 1 over x times the natural log of 10. But I need to plug in my inside function into here, which is going to be x squared plus 1. So again, this is going to be the derivative of log of x, but we've plugged in our inside function, and then we need to take all this times the derivative of our inside function. And again, we've got 1 over x squared plus 1 times the natural log of 10, and then we've got the derivative over here. Well, the derivative of the x squared is going to be 2x, the derivative of the 1 is going to be 0, so it's just going to be 2x, and we can simplify this as 2x over x squared plus 1 times the natural log of 10. And that's all there really is to it. There isn't a whole lot more going on with taking derivatives of logarithms. So let's look at maybe a slightly more complicated example. I want to take the derivative of log base 2 of x plus 1 over x minus 1. So here, again, what we'll do, just like normal, is we've got a log base 2 of x, and for our inside function, we've got x plus 1 and x minus 1. So let's go through this carefully. If I want to take the derivative of log base 2 of anything, it's going to be 1 over that anything times the natural log of 2 times the derivative of the inside function. Again, this is just the chain rule. I've got the derivative of log base 2 of that function times the derivative of that function. I'm going to come back to this in a second. I want to do this sort of by itself off to the side because this will involve the chain rule if I have to divide, or if I have this. So let's find. So this is my scratch work off to the side. Let's find the derivative of x plus 1 over x minus 1. So again, chain rule, we'll take, quotient rule, because this is a quotient, this is a fraction. We'll take the bottom squared, and then we'll take the bottom times the derivative of the top minus the top times the derivative of the bottom. And here we'll see that this will simplify down quite nicely. Maybe we'll make this a bigger fraction, x minus 1 squared on bottom. I've got x minus 1 times, well, the derivative of x is just 1, and the derivative of 1 is just 0. So that 0 is going to go away, and if we multiply anything by 1, it's just itself. So that's pretty simple. On the other side, we've got the x plus 1 times the derivative of x minus 1. Well, the derivative of x is 1. The derivative of 1 is going to be 0. And again, if you subtract 0 from something, it doesn't change it. If I multiply something by 0, it doesn't change it. So if I keep simplifying here, I have an x minus 1, and I'm going to subtract x plus 1. And what you'll notice is that I've got an x, and I'm going to be subtracting an x. So So all this simplifies down to minus 1, so that's minus 2, over x minus 1 squared. Whew. So that was a lot of work, but that's what my derivative is. So now I can start really simplifying this guy. So I've got, so that was some scratch work. So if I come back up here, I've got 1 over x plus 1 over x minus 1 times the natural log of 2 times negative 2 over x minus 1 squared. And this we can simplify a little bit. So 1 times negative 2 is going to be negative 2. And then on the bottom, if I just multiply straight across, 1 factor of x minus 1 will cancel with 1 factor of x minus 1, and I'll get x plus 1 times x minus 1 times the natural log of 2. And that's that. So we simplified all of that down to get this guy. And the one thing that I want to point out is that we did a lot more work than we actually needed to, because we know how logarithms work. So I'm going to show you the quick way to do this. So if I take the derivative, so let's see if I can fit this into one line. I probably won't be able to. I want to take log base 2 of x plus 1 over x minus 1. This can be pulled apart into 2 separate logarithms because we know our rules of logarithms. And if we subtract logarithms, we end up dividing their insides, dividing what's on the inside of these functions. So this right here is going to be a lot simpler to take the derivative of than this guy with this nasty quotient rule on the inside. We did all that work and we got it to simplify down quite nicely, but it turns out that a lot of this we didn't need to do. And in fact, and this is something that I suggest that you try on your own, take the derivative of both those guys and subtract them and see if you can't get it to simplify down to this guy. It will work. There's maybe one extra step in the middle where you have to find the common denominator of 2 fractions, but ultimately there is a simpler way to do this. Both ways absolutely work, so don't worry about too much if one way doesn't necessarily make sense.